Okay, so picking up where we were last time, we were looking at this example, and this example, we already did most of it, right? The big point to this was that by taking our vector field and computing the divergence, getting 0, we concluded surface independence, right? And surface independence is what allowed us to take the original surface we've been given and throw that away, and instead decide that we'd like to use this surface instead. Right? The key requirement, of course, being that you do have to keep the same boundary, right? So this boundary curve we did have to retain. So we can't, when we say literally, you can pick any surface. It's not quite literally any surface. You do have to maintain the boundary. Okay, so that was the broad strokes of this example from last time. What we did not talk about was orientation. And so that's what I want to finish up with here. Recall that our original surface, this surface right here, was given as being oriented downward. Now, there are two different orientations to choose from for a surface like this. There is one orientation, namely a bunch of normal vectors perpendicular to the surface. And then here's our other option. Something like that. And again, the language is never going to be precise. It just needs to be unambiguous, right? And of these two orientations, there's really only one that you could conceivably interpret as being downward, right? All the green vectors are pointing somewhat upward. All of the orange vectors are pointing somewhat downward. So downward obviously means the orange one. Okay, so that having been noted, we can talk about the induced orientation on the boundary. So again, our boundary is this curve right here. And we have a rule for how you take a surface orientation and induce a boundary orientation. The rule is with the right hand, thumb in the direction of the normal vector, and then you look at the way your fingers swirl. Okay, so this is hard to visualize. It's a three-dimensional thing, and we're looking at a two-dimensional picture, right? So that is hard. What I'm going to suggest, let's try looking at it a little differently. I'm going to think about the part of this surface kind of along like this, right? And I'm going to consider a point, let's say about right there. And in particular, this point I'm talking about is on this near side of the surface. I'm not talking about the back. Right? It's hard to draw that on a screen, of course. But at that point, the vector goes inward. So let me take a stab at how to draw inward here. Maybe something like that. It doesn't come on very well, though. But now, we're going to play the game. Right hand, thumb. I'm going to point my thumb in the direction of that normal vector. Let me do it a little bit out of the way. Thumb in the direction of that normal vector. And you see my fingers of my right hand, and they're making a swirl that is kind of like that. So that's the direction of the swirl on that part of the surface, and that intersects that side swipes up against our boundary curve in that direction. Everybody on board? Okay, so we have now an oriented boundary, right? The whole idea is now we need my new surface to not only have the same boundary, we need our new surface to have the same oriented boundary. So now it's easy enough to say, okay, well, if we forget about that, the original surface, I don't need the original surface anymore. And here's my new surface. My new surface is this thing. Let's say I'll use green here. And I just have to ask myself, which way does this get oriented? Should I orient it upward? Or should I orient it downward? The way we're going to resolve this is by remembering I've got to orient it in such a way that its induced boundary orientation has to be exactly the same as what came from our original oriented surface. So I guess we'll just try these one at a time for dramatic effect. I'm going to start with the one that isn't going to work. Let's start with this, and we play the game. Our new surface, if it were oriented upward, right hand, thumb, fingers, swirl, would swirl like that, which would sideswipe that way, which is wrong. Right? My original surface oriented my boundary that way. This, shot in the dark, coin flip, right? Random attempt at an orientation of my new surface orients me the other way on the boundary. So that's clearly wrong. So let's get rid of the, well, anyway, we'll just do that. Now we'll entertain the possibility of going down as my normal vector and play the same game. Again, right hand, thumb, in the direction of your surface orientation. Look at the direction that your fingers are sort of pointing around your thumb. That makes a swirl. The swirl is like this, which sideswipes the correct direction. Exact same orientation that our original surface gave us. And that's how we know that our normal vector is what I have pictured. Our normal vector is indeed downward, and thus 0, 0, -1. Everybody see how that works? It's just you got to be careful about this and just entertain your two possible. Step 1, figure out what your boundary orientation needs to be, and step 2, consider your alternatives and see which one works. One of them will work. One of them will not. Exactly. Okay, so that's all we needed to finish up. And now we're going to move along. The next thing to do, I guess what I should say first is we're actually kind of done with the Chapter 7 material in terms of new ideas in Chapter 7. Y'all will recall I have this diagram that I'm a big fan of, and I want to spend some time talking through the kind of two diagrams. And there's specific patterns that I think are really, really useful to notice for a couple of different reasons. So let me just get right into that. And I'm going to do this work on my typeset version of this diagram, because it's a little bit more thorough, a little bit easier to read, arguably. So anyway, here we go. First thing to observe. Well, okay, let me rewind a little bit. Where did this diagram come from? I did not make this up out of thin air. Right? Where I got this from was I took some very sophisticated constructions that were so elusive that mathematicians didn't figure them out until the early to middle 20th century. Right? This is very recent stuff in the big scheme of things. As I like to say it, I know people who knew the people who did this. Right? So this is recent. So those sophisticated ideas that eluded Gauss, that eluded the big mathematicians of their day, is too sophisticated to talk about. But if you boil off all the formality, this is kind of what's left. So don't think of this as just one person's kind of take on how to organize these ideas. This comes out of a very powerful, proven way of organizing these ideas. And again, just minus the formality. Okay, so here is an example of beautiful symmetries that come about if you organize things this way. Recall the fundamental theorem of line integrals, and there's this sort of pattern that you can write. Gradient goes that way, boundary goes this way, and if you evaluate the original function on your boundary points like so, or if you evaluate the line integral of your gradient over your original curve like so, then you get the same thing either way. And we made that observation previously that there was this little diagrammatic representation in some sense of the fundamental theorem. Just to streamline this process, I like to I like to streamline it like so, a little bit easier to write down. And I've shown you how this pattern holds with Green's theorem, but we haven't really talked about this again since we finished up talking about the three-dimensional stuff. So let me just, for the record, this pattern that works for the fundamental theorem of line integrals in 2 dimensions and in 3 dimensions, and that works for Green's theorem, is also a perfect representation of what happens with Gauss's divergence theorem, for example. We're taking a vector field and its divergence. We're taking a 3-dimensional solid and its boundary surface. And here we evaluate on the left, here we evaluate on the right. You get the same thing either way. Exact same pattern. Now, the stunner of it all is this theorem over here is about vector fields and divergences and solids and surfaces and stuff like that. And yet it has the same pattern as this unrelated theorem over here about gradients and boundary, curves with boundary points and line integrals. None of the players here are the same as any of the players over here. And yet the pattern is exactly the same, right? So that's it's pretty weird, right? That I think the fact that this pattern holds should persuade you that maybe organizing these players in this way, maybe there's something to that, right? And again, there absolutely is. There's a lot of deep ideas underneath all this. And then likewise, Stokes's curl theorem, same deal. Yeah, again, geometrically different story. Yeah, we're talking about a 2-dimensional surface and its 1-dimensional boundary curve. We're talking about a vector field and its curl, right? But the pattern, the resulting theorem, morally the same. Okay. All right, so we've talked about all that. Reminder, we've talked about what I, in Chapter 3, called lifetime theorems, and that elsewhere I've called local tests. So, for example, if you want to know if there is a function whose gradient is a given vector field, the way you arbitrate that is with the curl. And you look and you see, do you or do you not get 0? The way I've got this represented on the diagram here, and this is just a made-up notation that I totally made up, and don't overthink this. I'm using solid lines to represent the hypothesis. And then I'm using dotted lines to represent the conclusion. And so what this line right here, for example, says is if you have a vector field that is a gradient of a function, that's the if, right? That's the hypothesis. Then the conclusion is, well, the curl of that vector field is 0. Okay, so all of our local test, lifetime theorem, however you want to say it, stuff is represented by these lines here. And again, it's just kind of a way of thinking about this, the metaphor that I came up with for Chapter 3, that, the lifetime, everything has a lifetime of 2, is a pretty nice way to summarize that. Okay. All right. Yeah. So let's talk about the special vector fields. This is actually a related idea. Remember, there are certain special fields, special vector fields in this position right here. Special vector fields that, for example, you might want to compute a line integral of. And what's special about them? Well, they are gradients, aka they have anti-gradients. Another special thing about them, same vector fields. Curl is always 0 for all of these special vector fields. What else is special about them? They're path independent, and this is how I write that. This is just a choice, but any 2 curves with the same boundary points will give you the same value for the line integral. So, again, don't overthink the notation here. This is just kind of a way of representing players in our story on a diagram that I can draw a picture of. That's all it is. Just an organizational method. Okay, so again, there are these special vector fields. Cannot emphasize enough. These are not every vector field These properties apply only to these very restricted special vector fields. Okay. Right, so by the way, here, let me go ahead and while we're at it, I want to document on here how we drew some of these conclusions. And I'm not going to go over the ideas again because we don't have the time, and we've already done it. But if you want to know, how did we connect these dots? How did we know that gradients and path independence were related? And if you look back, you'll find that it's the fundamental theorem of line integrals was the tool that allowed us to relate gradients to path independence. And then if you also ask, how did we relate path independence to irrotational vector fields? Not vector fields where the curl is 0. How did that work? Well, the key idea was Stokes' theorem. And you can just look back through our notes and find where we made those arguments. So what we have then on this diagram, special vector fields, 3 different features that they have, and 2 different theorems showing how those features are connected. So this is a diagrammatic representation of just a ton of stuff that we talked about over a significant amount of time. Why do we care that this shows up on the diagram? Well, just as you may be wondering, this pattern holds. If you, there we go, close enough. This pattern holds if you just slide it over one dimension. It's amazing that this is true. But so here we go. The special vector fields at this point in the diagram, vector fields that are curls. Vector fields for which the divergence is 0. Vector fields such that any 2 surfaces with the same boundary curve give you the same flux, aka surface independence. All the same vector fields. And furthermore, look back through the notes if you don't believe me, but how did we show that being a curl related to surface independence? How did we connect the green to the orange? It was Stokes' curl theorem. How did we connect surface independence to divergence being 0? It was Gauss's theorem. So not only do the properties slide over with perfect symmetry, right? But the arguments that we used to connect those properties slides over with perfect symmetry. Roughly speaking, what this is telling you is that anything that you understand about arguments about path-independent gradient vector fields represented on the diagram, slide it over, that will tell you exactly how to make your argument, about analogous argument about surface-independent vector fields in a morally equivalent way. So really, really, really strong analogies. Okay. Pausing. Questions? Okay. All right. How are y'all going to use? Oh, yeah, question. Yeah.
I have a question. If you scroll down a little bit, what does G represent? Is that just another?
This is just a placeholder. So looking at this line right here, for example, that line, all this line says is, now keep in mind the solid line is our hypothesis. So that's saying, hey, if you have a vector field, let's just call it G. If you have a vector field G and its divergence is 0, then the conclusion is that that vector field G is the curl of something. So it's just a placeholder. Yeah. Okay. All right. Okay, so how are y'all going to use this? And look, I do think that there is something to be said. This being a liberal arts university and all, right? Something to be said for being aware of huge events in significant fields, right? So the bringing together of the 19th century theorems about Stokes' curl theorem, Gauss's divergence theorem, being able to bring them together and realize that they're closely related. It's a pretty significant cultural point. I think it's a nice opportunity to know that something like that did happen, and it is cool that it works, right? But this will also help you remember the theorems, because again, you don't have to remember a bunch of independent, sort of randomly strewn about your head, around your mind results. They fit together in an organized fashion. And so you don't have to remember results, you need to remember patterns. Right? You remember one pattern, you just remembered 6 theorems. That kind of thing. Right? And then the last way that you're going to use this, and that's what we're going to spend the rest of our time talking about today, the diagram interpreted appropriately will guide you toward how to solve computational problems. Right? And that's going to be our big focus for the rest of today. Okay, so let me get back to the notes, and here's our first example. Roughly speaking, this is how you should proceed whenever there is a question that asks you to compute a line integral or a surface integral, such as example 1 here says compute a line integral. Okay, what do? Well, you know a bunch of theorems that apply to line integrals. Should I use Green's theorem here? Well, I've got so many tools in my toolbox. Which one is the right one for this circumstance? So what you're going to do is follow this pattern right here. Step 1, identify where you are in which diagram. Talk about that in a moment. Next, do what the diagram tells you to do. Talk about the details in a moment. That'll allow you to draw certain conclusions. And then, having seen what the diagram suggests, all you have to do is just, as always, be on the lookout for geometric good fortune. Sometimes you get lucky with the geometry, right? We saw spheres have some really nice coincidences that happen. Planes are nice in certain ways, etc. Always be on the lookout for symmetry. So, yeah. Okay. So let's go through the details here. What do I mean by context from the diagram? Well, in this question here, notice our vector field has 3 coordinates. Well, apparently this question's in 3 dimensions. Notice our parametrized curve, 3 coordinates. Again, reinforcing what we already knew. This is a 3-dimensional question. And in particular, we are looking for a line integral in 3 dimensions. So back to the diagram. Whoa, I hit the wrong button. Back to the diagram here. Forget about this stuff. This is for R2. This is not going to be useful for our computation. That's 2-dimensional stuff. Can't use it. Okay. On the other hand, here we are, 3 dimensions. We want to compute a line integral. Line integrals are right there. And so that's where we're at. And that right away gives us a couple of candidate, hypothetical, with details to be checked, of course. But maybe the fundamental theorem of line integrals might work. I don't know. Maybe it's possible. You can see that sometimes that does work. And so we're going to have to think about that possibility. And, hey, maybe Stokes' curl theorem might, possibly. I don't know. Details to be checked. So we have a couple of candidates. We have already ruled out the Green's theorem. It's in the wrong universe. Green's theorem just doesn't apply here. And here's another thing we've ruled out, and this is very important. There is no way that Gauss's divergence theorem is going to help us on this question. Right? Gauss's divergence is way over here. Right? We're interested in a line integral. We have a curve. Right? Any vector field integrand we have is over here. Right? It's just not going to have anything to do with any of this stuff over here. Now, the reason I point this out, keep in mind when it comes to exams and how exams get graded. How is a grader going to come up with a score from looking at your work? Y'all have heard me say it a million times. It's not about the answer at the bottom, right? We're going to look at what you write and try to figure out, try to assess, okay, does this student have a good understanding of the relevant ideas, right? And while you're trying to portray yourself as having a good understanding of the ideas, right? Try not to make yourself look bad is always a good rule. So specifically, on a question like this, line integral in R3, none of this stuff could possibly be relevant, so don't put it on your page, right? Don't talk about divergence on a question about a line integral in space. No way that could possibly be relevant. It's a bad look, right? It makes, kind of makes it look like maybe you don't understand what divergence is for. Again, we're trying to get inside your head. We're trying to see what you understand. We're going to be speculating about how much you understand. And so again, bad look is not going to help. Likewise, please no triple integrals, right? No three-dimensional solids. None of that has any chance of being relevant. Does that make sense? All right. So a good thing to be on the lookout for. The diagram is what helps us with that. Right? Okay, what else to do? The little instructions that we have down here say compute the appropriate operator and boundary and infer consequences. Okay, well let's do as we are told. What is the diagram telling us to do? I'll come back to this stuff. What is this diagram telling us to do to our integrand? Well, our integrand is a vector field there. This spot in the diagram is the input to this operator. The diagram is telling us to compute the curl of that vector field. So we're going to do as told. We're going to compute the curl of that vector field. Now, after that, we're going to take our curve that we were given, and again, doing as told, we're going to compute the boundary, or we're going to identify the boundary of our given curve, because the diagram tells us to. Is everybody with me? All right, let's see what happens. Taking this vector field, let's compute the curl as instructed. And let's see here. Now there's various, y'all remember the formula for curl, right? It's the symbolic cross product, which itself is a symbolic determinant, and there's various partials to compute and subtract from each other. Make sure you remember those details. Make sure you're proficient with that, right? And it turns out, if I remember correctly, that in fact we get 0. Okay, now, so what? Is that a good thing? How does that help us? What do we conclude from that? Well, back to the diagram. As instructed, we computed the curl. We got 0. And now we recall from our many properties that we know about what happens when curl is 0. Among them, there is a function whose gradient is that vector field. AKA, there is an anti-gradient for our vector field. Yeah? Everybody good? So that pretty much, by the way, already tells us that we're on the board. We have an option. Fundamental theorem of line integrals would totally work. Now, what are our other options? Yeah, I'll try to identify all of our options before we nail one down. But computing the curl, getting 0, inferring that there's an anti-gradient, we know that this is a candidate. This does apply, not just hypothetically. This does apply to our question. Okay, let's look at the boundary story. Let's see here. What happens if we look at the boundary of our curve? Okay, well, here's our curve. It's given parametrized. It's a little weird. There's a bunch of different ways that you can have a curve be presented to you. It could be described geometrically. It could be parameterized. Who knows? Right? But I can tell you where the start and end are by just taking the starting value of t and plugging it in. And then I'm going to take the ending value of t and plug that in. And let's just see what we get. Plugging in t equals 0, I get 0, 1, 1. And now plugging in t equals 1, I get, let's see here, cosine of pi is, okay, so minus 1, 1, and e squared. Okay, so this is our boundary. This curve has a starting point and an ending point. So what? What does that tell me? Well, just figuratively, it starts at one point and then it ends at another point. So let's entertain the question then of, hey, is this curve a boundary of something? Nope. Right? This is a terrible sheep pen. Right? If this is the pen that you build to keep sheep in, you're not going to keep them in. There is no in. Right? So this is not a boundary. Is everybody happy with? Okay. All right. So back to the diagram. We did not get 0. We did not get the same point at the start and the end, which effectively means no boundary at all. And that means that there is no surface whose boundary is that curve. Or as I like to say it, this curve does not have an anti-boundary. Right? All right, so that means Stokes' theorem is out. Forget about it. Right? Remember, Stokes' theorem only applies if your curve, says right there, is a boundary of something. And specifically, whatever it is a boundary of, that thing that your curve is a boundary of, that's going to be the domain for your new surface integral. So, not only can I not compute my line integral with this surface integral, there is no surface integral. Because there is no surface. Because our curve does not have an anti-boundary. Because our curve is not a closed curve. Everybody follow that? Okay. All right, so again, here's what we've been able to conclude. The diagram gets credit for all of this. Right off the bat, Gauss's theorem out the window. Forget about it. That's silly. Some non-trivial reasoning allows us to realize that we should not be wasting our time trying to write down Stokes' theorem here. Wouldn't make any sense. There's no surface to even talk about. So that's not going to happen. But the fundamental theorem of line integrals would totally work. So we have successfully diagnosed this problem. Right? This problem that we were just looking at here, this is a fundamental theorem of line integrals question. So compute the anti-gradient. Remember, we have a game to play that allows you to compute anti-gradients. And then line integral, just f of b minus f of a. Plug and chug, yes.
So if you evaluate your parameterization at like 0 and 1 and you get the same value, is that enough proof that you have a boundary?
That's enough to show that your curve is closed, which shows that it is a boundary of something. I'm going to put a little asterisk there. Formally speaking, there's some issues, but it doesn't apply to us. And yeah, in fact, the very next example, we're going to see something like that. Yeah, yes?
Why did you, on our diagram, cross out the path from curves to points?
Let's see here on on the what now?
Right. Why is the curves to points arrow crossed out?
Oh, I just meant that it wasn't 0. Yeah. So you're talking about this right here.
Yeah.
Yeah. So the what I'm indicating here is that the question was, is the boundary there or is the boundary nothing? And the boundary is there. I could have concluded, I would have had an anti-boundary surface had the boundary been nothing, but the boundary wasn't nothing, and so I used an X just to represent that it's not 0.
Gotcha.
And being not 0, there is no anti-boundary surface. That's all. Yeah. Okay. All right. So I'm going to let y'all work out the details on that. My goal here is not to show y'all how to do plug and chug calculations. Y'all are good at that. I'm willing to believe that. But how to diagnose, and we have successfully diagnosed our first question. So we went through this process. Okay, let's do it for this next example now. Okay, let's see here. Context. 3 coordinates for our vector field, 3 coordinates for our parametric curve. This is clearly in 3 dimensions, and furthermore, we are looking at a line integral in 3 dimensions. So on the diagram, this is a same deal, right? We're in R3, we're looking at a line integral, so there's our context. Again, no Gauss, no triple integrals, no divergence, has no chance at all of being in any way relevant to the calculation we've been asked, so we leave all that conspicuously off of our work, right? Good look and all that. Okay, so our vector field, we need to take the curl. Our curve, whatever that is, we're going to need to think about its boundary. Diagram tells us so. Right? So let's do it. Let's see here. Looking at our vector field, we compute the curl. And we get 0. Now that's, again, a bunch of partial derivatives, and I'm going to leave you all to do that. What you're going to notice pretty quickly, by the way, and I think this is a good little sort of, little shortcut to remember, all of the partial derivatives, when you compute curl, they're all what you might call off partials. So the first coordinate, there will be a y partial of that, there will be a z partial of that, but there won't be any x partial when you're computing the curl. Right? So they're all kind of... The first coordinate of the vector field, in computation of the curl, you won't take the partial with respect to the first variable. So since they're all off partials, and the first coordinate is all x's, the second coordinate's all y's, the third coordinate's all z's, you kind of instantly know all these partials are going to be 0. You can notice that as you write it out, as you work out those partials. Okay, what does that tell us? The curl is 0. Back to the diagram. The curl is 0. That means there is an anti-gradient. That means the fundamental theorem's on the table, and we've got a candidate. We could conceivably do it that way. Let's finish filling out our options, though. We're now going to think about the boundary of our curve, and is it a closed curve, etc. Okay, well, our curve, all of this. Plug in t equals 0, you get 0, 1, 1. And now you plug in t equals 1, and you get 0, 1, 1. How about that? This curve starts and ends at the same point. Yeah? Okay, so let's now again, just figuratively speaking, there's my starting point, and it goes off and does a bunch of stuff, and then there it ends at this same point. That is a good sheet pen. That is a closed curve. That is a boundary of something on the inside. So that means, going back to my diagram here, from the fact that there is no boundary, I conclude there is an anti-boundary. And that means that Stokes' theorem is on the table too. And you can do either one of those. You can make an argument with the fundamental theorem of line integrals. You can make an argument with Stokes' curl theorem. Take your pick. Oh, and of course, as always, you also could just plug and chug directly. And sometimes, by the way, that is the best answer. Sometimes finding the anti-gradient, even if it exists, might be laborious. Sometimes your new surface might be hard to get your hands on or something. So I don't want to suggest that whenever one of these theorems applies, it'll automatically make the problem easier. Right? It just gives you another option. And sometimes just computing the thing that you were asked to compute directly, sometimes that is the easiest of your 3 options. So we kind of have 3 options here. Now, I do want to point out, in this case, our 2 new options are both pretty awesome. And I strongly suggest that we not parameterize or take our original parameterization and work with that. That'd be brutal. But look how easy, in this case, it would be to apply Stokes' theorem. This original line integral, Alternatively, I can compute the flux through whatever the anti-boundary surface is. I don't know how to write it down, but I know it's there. I know there is some anti-boundary surface. And on that surface, I'd be computing the flux of 0. Obviously 0. So pretty sweet, right? So Stokes' theorem works out great. The surface, I don't know about that, but the vector field is easy. So really nice computation there. Now let's think about how would it go down if we were going to use the fundamental theorem of line integrals here. Well, we'd be plugging into this formula, namely at each of our boundary points, we'd be plugging into our anti-gradient function. Again, the diagram organizes this for us. And here's the thing. These 2 points, the starting and ending point, same point that you're plugging into whatever your anti-gradient is, whatever this anti-gradient function is, you're going to be plugging the same point in twice and then subtracting. You're going to be subtracting some value from itself. And again, a freebie, easy calculation, you get 0. You don't even have to compute the anti-gradient. It's f of something minus exactly the same thing. So, again, much easier. Now, to be fair, yes, you could plug and chug original, but that's going to be a brutal calculation, right? You can see that in the statement of the question. Let's see. This nasty vector field where that is your x and that's your y and that's your z. Oh my God. Right? I want nothing to do with that. Okay. How we doing? All right. Okay. Next example. Still 3 dimensions. Still a line integral. Same context then. Let me clean up our picture just so I can reproduce. Let's see here. So we're still looking at a line integral in R3. We're going to take our vector field and compute the curl, see what we get. We're going to take our curve, think about the boundary, see what we get. Draw corresponding conclusions, making sure not to even entertain the thought of doing any of this stuff. That's all out of the question. Okay. So we compute the curl. Let's see here. So this vector field, you compute the curl, and you get, as it turns out, -1, -1, -1. I just happen to remember that from the lecture I gave an hour and a half ago. But again, make sure you can do these computations. Make sure you know how to use the curl. What does this mean? What do I conclude from the fact that this is what it is? Well, it's not 0. And so since it is not 0, that means there is no anti-gradient. That means fundamental theorem is off the table. Out of the question, not going to happen. Don't try. Doesn't apply. Yeah? Everybody happy? Okay, well, let's think about that curve. Okay, this is weird, right? Our curve is the intersection of a couple of surfaces. On the one hand, I have a cylinder, and on the other hand, I have a, didn't want that. On the other hand, I have this plane, and how does a plane cut through that cylinder? Well, that intersection, our curve, geometric appeal, right? Just how does a plane cut through a cylinder? Well, it's going to give you a kind of a tilted ellipse. Everybody buy that? So what can I say about this tilted ellipse? Where does it start? Where does it end? Well, it kind of doesn't. Right? It doesn't have a start or an end, or if you really want to, you could say, like if I were to parameterize it, I guess I could arbitrarily pick that it starts here, but then that would mean I would have to end there, and effectively there is no boundary. And so again, back to the diagram, I do get 0 for its boundary. That means that there is an anti-boundary surface. That means Stokes' theorem is on the table. And we can do this with Stokes' theorem. So, your options on this question are plug and chug directly, not outrageous, or rewrite as a flux of the curl through a new surface whose boundary is your given curve. And let's talk about how to find that surface. Looking at our situation here, what surface can I think of whose boundary is this curve? Well, a surface, I guess, is options, but I think this would be the best choice. Take that right there, namely the part of that plane that's inside of our curve. So you can use that surface and compute a flux of the curl. Here's the curl. Or you can parameterize and plug and chug directly. Is that cool? Now there's a bunch of details in there. I think this is a good exercise. I would encourage everybody to do this, to try both of those options and see which one you like better. And by the way, I'm going to be distributing some videos when I get back to my office in a few minutes here, where in past semesters, I've recorded extremely detailed discussions of all of these 6 exercises. And so all the stuff that I'm saying, yeah, go ahead, a lot of that I will do for you in those recordings if you want to see how that works. But we have 2 reasonable options, and frankly on this one I think they're about equally convenient. Okay, next one. This will be the last one we have any time to do. It's pretty similar. We have a vector field for which we've already computed the curl. It's the same one as the previous exercise, so that's that. Let's see, now we have a curve which looks, again, pretty similar. We have clearly a cylinder and a plane again. Now this is a different plane. And that intersection again is going to be kind of an ellipse. Something kind of like that. Which of course will have an anti-boundary surface. Now all of this is diagrammatically the same because, well, it's the same. Practically everything is the same between this and the previous example. The only difference is this is a different plane. And it turns out this makes a tremendous difference. So this is an example of what I was talking about always keep a lookout for good fortune. Sometimes you get lucky. Sometimes life is good. And you want to be able to capitalize on those. Every single time something lucky comes up, you want to be able to score that, right? So here's what's nice about this. Let's rewrite our integral. Let's see here. Let's rewrite our integral with Stokes' theorem. Flux, curl, dot ds. Right, that's how we write curl. Now, I'm going to choose, in this case, because it's going to work great, to rewrite my ds as little n ds scalar. And let's talk about this little n. What can I say about color choices? I guess I will use dark blue here. What can I say about that little n? Well, it's the normal vector for my new surface. Right? We're doing a flux over the new anti-boundary surface. That surface is this thing right here. So there's the normal vector. But check this out. That surface is entirely inside of this plane that has this equation, which therefore allows me to instantly write down a formula for this normal vector. This normal vector is, there's some orientation questions to maybe we might have to worry about. But read it right off of the equation for this plane. coefficients are 1, 0, -1. And again, we'll worry about orientation if we have to, but 1, 0, -1 right there in the equation for the plane. So let me write that down. 1, 0, -1. And of course I need it to be a unit vector, so we'll normalize it. And we win. Right? You look at our new integral here. Curl dot little n. There's our curl. There's our little n. And this dot product, 0, the whole thing disappears in a puff of smoke. And Stokes' theorem is an awesome way to solve this problem. Again, you could parameterize it, you could brute force it, and I guess that would kind of work or something, but Stokes' theorem makes it easy in this case. So always be on the lookout, right? I mean, you're going to have to compute curl anyway. When you see something like that, when you see that your surface is flat, that's a potential for awesomeness, and just write down that normal vector real quick, right out of the equation, and see if you don't just get super lucky. Okay. All right. So we're out of time. We will we'll start with chapter 4 on Monday. Y'all have a good rest of your weekend. And let's see here.